Welcome everybody. I apologise for talking to a room full of German people in English, but as an Englishman, our foreign languages skills leave much to be desired. I'm very sorry. So I'd like to talk a little bit about the rationale for continuous delivery. I'd like to talk to you about why I think this is an important change in our industry. I think that we talk often about change in our industry. And I think that's fair enough. There's a lot of change that goes on, but I think that there are times where there are significant changes, and I believe that this is one of those things. I think this is a significant change in that it changes our view of what software development is. And I hope to, over the next 45 minutes or so, give you some indication of why I think that. I think a good starting point is to start looking at the history of our industry and a little bit about what the kind of success rates of software projects. And on the whole, given that you should probably take these sorts of things treat these things with a degree of skepticism because they're not scientifically controlled experiments. On the whole, though, these sorts of surveys of software projects tend to tell a tale of disappointment and woe. This last one is kind of amusing in a macabre sort of way. 17%, in a survey of nearly 6,000 projects, 17% of them go so badly that they threaten the existence of the company that undertake them. That's not a story of success. I would suggest that if software projects were normal things, there ought to be a normal distribution of software project success, as many software projects ought to finish ahead of schedule, below budget, delighting their users, as finish over budget, behind schedule, and annoying their users. But I don't think this is what we consider normal. I think what we consider normal looks more like this. I think that we've become acclimatized to an industry where this is more like our assumption of what normal looks like for software projects. And that's actually quite profound. It's quite serious in its implications, because that changes the way that we think about starting projects. It changes the way that we think about funding them. It changes the way that our regulators think about measuring their success. It changes the way that we go into projects. And that's a problem, because if this is the distribution curve for software projects, it ought to be telling us that we're doing something wrong. I think we should expect a normal distribution of project success. This is a diagram showing two different pictures of the solar system. The first one over there, the geocentric view of the solar system, was the picture of the solar system that humanity held for thousands of years. It assumed that the Earth was at the center of the solar system. And when you assume that that's the case, you have to account for the orbits of the planets, which describe these weird shapes. It's complicated, it's difficult to reason about, it's hard to extrapolate from there, it's hard to figure out. Astronomers spent literally thousands of years trying to figure out the maths that would predict where the planets would go, and they saw these things called epicycles, where the planets looked to be going backwards at some points in their traverse of the skies. Then Copernicus comes along and he says, no, you've got it all wrong, the sun's at the center of the solar system. And at that moment, the model snaps to being much, much simpler. The problem is if you're living in that view of the solar system, Newton can't come up with an inverse square law. A few centuries later, Einstein can't come up with a model of space-time and bendy sheets of space-time that are affected by gravity wells. Those are not predictable outcomes from that model. This, on the other hand, this is where those ideas come from. This simpler picture allows us to extrapolate and reason. I believe this is a great analogy for where the software industry is. I think that a large part of software development is based on an entirely misguided picture of what software development is. And that's quite important. That's quite a worrying thought, but it's quite important, because I think that as soon as you get to a clearer view of what software development ought to be, things become simpler. Things become more easier to understand. The complexity of our processes diminishes. The kinds of things that we need to do to achieve success are simpler and more reasonable. I hope to convince you that that's kind of a reasonable analogy as we go through. So I would argue that the state of software development has kind of been somewhat suboptimal, to say the least. But I think in recent years, just the last few years really, that there have been signs of hope. Now, I chose this picture carefully. This is not a shiny production line, cookie cutter kind of solution. It's a bit home built, it's a bit home brewed, but it's clearly more efficient than the last picture. So let's look at how what we've learned from, and we've looked at other industries. We've taken a view, and we've looked at the processes and approaches that other industries have taken to complex processes, and we've looked at manufacturing industries, and we've come up with waterfall implementations. We've come up with V models. We've come up with dividing the problem up into a series of steps, which is sensible, but we've ended up building siloed organizations and incurring huge costs of handovers between different stages in the process. We've tried getting more iterative approaches to development. We've tried techniques like Scrum project management to allow us to manage our projects more effectively. We tried extreme programming. We've tried hiring really smart people and putting them in a corner somewhere. We've tried hiring teams of young smart people because they're cheaper. And we've tried hiring young smart people in foreign countries because they're cheaper still. And none of these are the solution. At least not alone. Here's one of the things that's part of the root of this misguided view of what software development is. This is the paper that introduced the idea of waterfall as a model for software development process. This was published in 1970 by Dr. Winston Royce, who was publishing it for a conference in the IEEE organization. And this is the document that introduces the idea of waterfall for the first time. This is the diagram that everybody's familiar with, right? Everybody's seen this diagram before. This is on page 2, and this is the next paragraph, which I'm going to blow up so you can read. The implementation described above is risky and invites failure. The testing phase, which occurs at the end of the development cycle, is the first event for which timing, storage, input-output, transfers, etc. are experienced as opposed from analysed, and these phenomena are not precisely analysable. So the paper that introduced the idea of waterfall to software development was saying, don't do waterfall. Unfortunately, we didn't pay attention. And you can kind of understand it, that the picture's nice and easy to remember. This is the picture that he was trying to recommend. Not so nice and easy to remember. If you read this, though, with the benefit of 21st century hindsight, there are a lot of interesting takes here. One of them is that testing must be planned, controlled, and monitored. It says that we should establish feedback loops from testing into program design and from program design into requirements. That doesn't sound much like a waterfall process. With the benefit of 21st century hindsight, you could say that sounds a bit like an agile process. It sounds like a bit like an iterative process that allows us to learn and adapt. Here's the relation to hafentalks. I was told that hafentalks refer to talks on the quayside, so here's a quayside. So here, this is a quayside in the west of Ireland. I was at a conference in the west of Ireland recently, and somebody came and said, "That's my cousin," but that doesn't matter. But there's a car that's fallen into the water. So what do you do in this kind of situation? A car's fallen into the water. You go and get a crane to lift it out. Damn! What do you do now? Bigger crane. Yeah. Yeah, what now? Einstein says that the definition of insanity is doing the same thing over and over again and expecting different results. I would argue that if our software development processes are not delivering the results that we desire, we should try something different. I would argue if they're not delivering the results that we desire, we should try anything different. I think a good place to start is this. I think that any organization that creates software wants this. They want to be able to have an idea, they want to be able to get that idea into the hands of their users, and they want to figure out what their users make of the idea. I think that's it. I think that it's hard to imagine any organization that creates software not wanting that. And so I think this is a good place to start. I think we should optimize to make that work. So I want to pose a question, and I'm going to show you some pictures that are meant to intentionally mislead you from the correct answer. Any ideas what's the greatest invention in human history? Please play along. Beer. I have beer. No, it's not beer. Although the beer is very good. The wheel, fire, excellent suggestions. Language, somebody said to me once. I think that all of those are really good ideas and wrong. I think it's this. I think it's the science, and by that I don't mean Large Hadron Colliders, space shuttles, gravitational wave detectors, modern medicine, any of that stuff. What I mean is the simple process of having an idea, theorizing what that might mean, designing a test to try it out, running the test and learning from the results. I think that's it. I think the scientific method is the most important invention in human history. If you look at the history of the human species, we've existed as a distinct species for about 200,000 years. The people 200,000 years ago were precisely the same as us from a biology standpoint. They had the same number of neurons in their brains. They were just as smart as we were. And yet, if you look at the history of our species, by almost any measure of advancement, it's a flat line until about 200 or 300 years ago. If you look at the amount of energy wheeled, the amount of information that we process, the number of connections that we make, the distances that we travel, the resources that we consume, all of that stuff, flat line until about 200 or 300 years ago, and then it starts to tick up. And then through the 20th century, it goes exponential, and through the 21st century, it just goes off the chart. It's a straight line, vertical straight line. There's data that says that the whole of human knowledge doubles once every 14 months. I'm not quite sure how you work that out, but it's a staggering idea, nevertheless, and it feels like it might be right, even if it's not true. So, what happened 200 or 300 years ago? What is the thing that gave birth to our advanced technological civilization? I think it's the birth of rational application of science and engineering. Here's the scientific method. This is what the Wikipedia says the scientific method is. We might make a guess based on experience and observation. We propose an explanation. We make a prediction from that proposal, and we test the prediction. That's it. That's the thing that gets us essentially out of, pre-industrial civilizations to the modern high-tech information age that we're in today. I think that software development is one of the more difficult things that we undertake as a species. We're dealing with this abstract, ephemeral stuff. You can't touch it, you can't weigh it, you can't measure it. It's fragile. We can put a comma in the wrong place, use the wrong sized variable holder for a value, and we can blow up a spaceship. We can lose $500 million in trading in seconds through a silly mistake. All of these sorts of things are what happens as a result of when software goes wrong. Wouldn't it be sensible, if it's genuinely one of the more difficult things that we undertake, to apply our strongest problem-solving technique? And I don't think we do. I don't think we apply this kind of thinking, this kind of thought to software development very much. Certainly in my career, much of my time I've spent guessing at things and trying things out and hoping that I was right, instead of trying a test, evaluating my hypothesis and learning from it. I would guess what features my users might want in the future, and hope to deliver them 6 months down the line or whatever. I would guess whether my design is going to fulfill the needs of those features and be able to deliver them. I would guess whether my architecture is scalable enough to be able to cope with the level of demand. I wouldn't test it. I would guess that that's going to work. Wouldn't it be better if we started to experiment? Here's some more data. These are the results from another one of those software project surveys, and this is the Chaos Manifesto, and basically it says waterfall's not very effective and agile's more effective. People say this is a bit depressing and not very, a bit too negative. One of the people that says that is Scott Ambler, who produces this picture. And this is my organization of his data. These are kind of planned sequential approaches to software development. These are iterative approaches. It amused me when the first time I saw this data is if you make up your software development process on the spot, slightly more effective than waterfall. I thought it was funny when I first saw it. The top line is where the interesting stuff is, though. And that's saying that these iterative approaches that give us opportunities to learn, essentially to experiment and try out ideas, are more effective. And lean stands out particularly as a strong process. So what's that about? It's not really surprising that this aligns well with my thinking, because lean was born from the scientific method. So when Edwards Deming went to Japan at the end of the Second World War and helped them help their industry recover after the war and introduced more effective processes to production engineering and so on, it was by directly lifting ideas from the scientific method and applying them to process improvement in those organizations. The total quality management, the Toyota approach to process, all of those things were born, the lean movement, all of those things were born out of Edward Deming's work. And so lean's about trying to get into this more experimental mindset, trying to try out ideas and trying to do that efficiently and effectively with the minimum amount of work. So we want to be able to deliver things quickly because we'd like to maximize our opportunities to learn. We'd like to be able to learn, make changes in small batches, try out those changes, find out what works and what doesn't, and then move on to the next change. If we want to do that, we want the change to be durable. We don't want to have to make a change and then have to go back and fix it because it's not very good. So we want to take quality seriously. We want to be building quality in all of the way through. We want to treat the process as a whole. We want to look at all of the process and not just optimize little pieces of it, but try and optimize the whole process from end to end and think about the flow of ideas, from an idea into the hands of users and figure out what they make of it and think about all of that and trying to optimize all of that. We want to eliminate waste. We want to be efficient. We don't want to do things more than once. We want to do things durably. We want to do things in a way that's going to make us more efficient over time. So we want to reduce unnecessary variations. We want to not overburden teams with too many features. We want to give teams time to understand the implications of their changes, time to do work that's going to speed them up. One of the fastest ways to slow a team down is by fully loading that team with a backlog of features. You must give the team space to refine their working practices, improve their own procedures, find ways of working more efficiently. That's some of the most valuable work that teams do. Teams that work at 100% capacity tend to go slower and slower over time. They tend to create lower and lower quality over time. And lastly, wasteful activities. We'd like to be able to concentrate our efforts on the work that delivers the most value. There's data that suggests that the best companies in the world, 2/3 of their ideas produce zero or negative value. If that's the case, then it makes sense to optimize our processes to be able to have lots of ideas and to try and identify the bad ones quickly so that we can discard them. We want to be able to work in a way where we can learn, understand what we're doing, build on our learning and move forward. So we want to amplify learning. Modern lean practitioners talk about optimizing teams by focusing on learning above all other outcomes. You don't focus on delivery and get good learning. You focus on learning and you get good delivery. We want to make decisions late. We'd like to make decisions when we have the most high-quality information. If we make all of the decisions early in the life of a project, we're going to be making the decisions at the point when we know the least about the project that we'll ever know. If we defer decisions until the last responsible moment, as a friend of mine calls it, my wife says that that's microseconds ahead of the first irresponsible moment, but that's another argument. But the last responsible moment, we will leave decisions until the last responsible moment where we hope that the quality of the information we have is going to make us have higher quality decisions. And finally, we need to empower the team. We need to put the team in a position so that the people that cause a problem are in a position to witness the problem that they've caused because they're going to be best placed to understand what they need to do to fix the problem and that they should have the time to do that. And so we want to make sure that development teams see the impact of their changes in production, that they're able to deal with those and they're able to understand what works and what doesn't work and they're able to move forward and improve the situation. Increasingly, I tend to think of software development like this. It's really about a series of interlocking feedback loops. And the more that you look, the more you find these feedback loops. I would strongly recommend that you take this to heart, and everything that you do in your professional life, start thinking about how am I going to understand the impact of this change? How am I going to understand whether this code works? How am I going to understand whether this change in my process works? How am I going to tell whether this reorganization of my team works? And try and figure out what the test is, what the experiment. When are you going to look at the results, and when are you going to get the feedback? At the technical level, I think this is quite a good model for software development. At the outside, we're trying to have an idea, get it into the hands of our users, and figure out what they make of it. At the inside, we're doing this tight cycle of test-driven development. Write a test, see it fail, write some code to make the test pass, tidy it all up, commit, move on. And then in between, we've got these executable specifications, automated tests that are going to validate the software from the perspective of the user to give us a strong assertion that the software is delivering the value that we intend it to do. This is, you can probably tell from the tone of my presentation that I'm kind of a bit of a popular science nerd. And this is Richard Feynman, who's a genuine first-class genius. Feynman was a Nobel Prize-winning physicist who came up with a way of doing calculations in a field called quantum electrodynamics. The tools that he created, the analytical tools that he created, the calculation tools that he created, make the most accurate predictions in human history. They are 3 orders of magnitude more accurate in their predictions than general relativity. And general relativity is kind of off the scale compared to almost anything else that we do. This is a first-class mind, a genuine genius, one of the finest minds that humanity's created. And he said, it doesn't matter how intelligent you are, even if you're as intelligent as him, if you guess and that guess can't be backed up by experimental evidence, then it's still a guess. We're technologists. We think of ourselves sometimes as engineers. So I think that we should be starting to apply this sort of thinking. We should be trying to think of how to apply an experimental technique. How do we start working not based on guesses, but based on tests, based on assertions, based on experiments? If that was all I had to tell you, I think there's some good stuff there. But I think there's some more. And one of the things that I think is really important in the context of continuous delivery is this stuff. This is the idea of cycle time. This is a proxy measure from having an idea and getting an idea into the hands of our users. And the idea is that what you measure is that you measure your software development process, the efficiency of it, or at least the latency of it. And so what you look to is imagine making the smallest change that you can think of to your production system. And now imagine that change going through all of the normal steps that it should go through to validate it before it gets into production. So how do you figure out that it's a good idea? How do you figure out that, how do you put it onto somebody's backlog? How does that get picked up by the team? How does that feed into their development process? How do they decompose that into tasks or whatever? How do they implement that? How do they test it? How do they validate it? How do they deploy it? How do they test that? How do they get it in, how do they release it into production? All of those steps. And you kind of measure all of those things, and you measure the delays between all of those steps. I'm going to show you 2 cycle times. The first one, both of these are software projects that I worked on. The first one was a project for a bank. This was an order management system for a bank, and the cycle time for that organization was 103 days. They couldn't release a single line change to their code in less than 103 days, and follow their own processes. If they had an emergency fix, they had to break the rules. If you've got a cycle time of 103 days, you don't have a feedback loop. If you've got a cycle time of 103 days and somebody comes back to me after 103 days and says, Dave, you've just broken production, I'm going to say, what? I wasn't here then. I was on holiday, couldn't possibly have been me. And I might be right. I'm going to say, anyway, it wasn't my change, it was my change and somebody else's change. It wasn't my fault, it could have been anything. How can we tell after 103 days? And I'm right. We couldn't tell. If you've got a cycle time of 103 days, what's going on is that the number of changes that are being released every 103 times is going to be huge. It's going to be very complex. It's going to be very difficult to understand what caused the problem. And I might be right, it might not have been my change, it might have been my change in collaboration with another change that caused some unforeseen circumstances. I'm going to show you another cycle time. This project, in terms of scope, was roughly 15 to 20 times more complex than the project on the top line. On this project, this was a whole enterprise system. This was one of the world's highest performance trading systems, an exchange for trading foreign exchange instruments. And all of the admin around that, all of the data warehouses, public APIs, public website, private connections to various third parties for clearing, for trading, for other things, admin consoles that allow you to operate the system, management information systems, all of that stuff was in the scope of this system. We could make any change to that system in production, and we could evaluate it, and after 57 minutes we would know whether that change was fit to release into production or not. There would be no more work to do after 57 minutes. If you've got a cycle time of 57 minutes, you're in a whole different game. If you've got a cycle time of 57 minutes, if somebody comes to me and says, Dave, you just broken production, I'm going to remember what I'm doing an hour ago. I'm going to remember what it was. The scope of that change is going to be small. It's going to be simple to reason about. If I've really screwed up, it's going to be easy to revert it, to pull it out. If I've got a cycle time of 57 minutes, then it's much, much simpler to figure out what's going wrong. I want you to pause for a moment and just think about the riskiness of these two processes, because one of the pushes against continuous delivery is often that you're talking about releasing all of the time. That's really risky. Actually, it's not. It's the reverse. If you think about the risk encompassed with a bunch of changes, and imagine there's a whole bunch of changes, there's going to be a little bundle of risk associated with every individual change. And so adding up all of those risks is going to be the sum of those risks. And then you've got an exponential function of some kind. There's the combinatorial effect of different changes, the chance that two or more changes might interact with one another and cause a problem. That's going to be some kind of exponential function. And that's going to be added into the equation as well. So if you've got a whole load of changes, then the exponential bit is probably going to dominate in terms of the riskiness. So you have a big lot of additive stuff, but then you've got this exponential bit at the end. If you've got a small number of changes, if you're getting to a releasable state once every 57 minutes, you've probably got 4 or 5 changes. There's a relatively small bit, exponential bit, and there's a relatively small additive bit. So on the whole, this is a low-risk strategy. We'll talk more about that as we go on. I think this stuff is really important. I think that if you stopped now, if you all went back to your software projects and you took my advice and you worked to optimize your software delivery process, just optimize the cycle time, to work just to reduce the cycle time, nothing else. If you did that in an experimental, iterative, empirical approach, I think that you would drive out all of agile theory, all of lean theory, all of continuous delivery, all of DevOps as a natural consequence. All of those things, you can't have a cycle time for a complex system of 57 minutes without being great at all of the things that you need to be able to do to deliver software. You've got to have a good mechanism for flowing ideas and identifying their value and getting them through. You can't have a cycle time of 57 minutes if you have a large team. The communication overhead will kill you. You can't have a 57-minute cycle time if you have a siloed team. The handovers will kill you. You can't have a cycle time of 57 minutes if you haven't got a great story on automated testing, automated deployment, automated configuration management, monitoring. All of those things must be in place. You've got to have a good architecture. You've got to have reliability in your tests. All of those things must be in place to achieve a cycle time of 57 minutes. It drives good behavior. It's not a silver bullet. It's really hard to get down to that kind of level of assertion. You've got to change the way in which you think about things. You've got to change your mindset, the way in which you approach things. We're talking about a paradigm shift in thinking here. So let's get into that a little bit. So what are we talking about? So continuous delivery to start with, it's the first principle of the Agile Manifesto. It's the logical extension of continuous integration. If continuous integration is a good thing, we kind of just extend the range of that a bit further. I like to think of it as this holistic approach to software development. If you want to genuinely get down to these really short, effective cycle times with a high level of confidence in the quality of the work that we're doing, then you've got to consider all aspects of the development process. You've got to think about testing, deployment, automation, configuration management, all of these things. A good mental model for this is imagine every time that you commit a change that's destined for production, whatever the nature of the change, we're giving birth to a release candidate. And the job of our continuous delivery system and process is to prove that that release candidate is not fit to make it into production. That sounds backwards at first, but this is another one of those lessons that we will learn from science. We can never have enough tests to prove that our software is good. But as soon as we have one test that fails, we know that our software is not good enough and therefore we should not release it. We use tests as a falsification mechanism. What that says is that we've got to treat test failures seriously. It means that we can't afford flaky tests. It means that we can't afford to live with test failures and kind of say, oh, it looks okay, we'll release it anyway. We need to get to a place where we can use the tests as a falsification mechanism. I would argue that tests that are passing are telling you nothing. It's only the tests that are failing that tell you anything. And if you ignore them, what are they telling you? Finished means released into production. Actually, that's not quite enough. Finished means in the hands of users delivering value. Released into production is a bit too soon. So we want to think about the whole value chain. So we're trying to create a repeatable, reliable process for software release. If we want it to be repeatable and reliable, sorry, it kind of rules us out. As a species, we are not good at repeatable and reliable. So if we want things to be repeatable and reliable, then we need to automate pretty much everything. If we want to automate everything, we've got to keep pretty much everything in version control. We've got to be precise, not just about our source code, but about the environments that it operates in, the version of the languages, the libraries that we're linking with, the relational databases that we're running against, the web servers that we're running, the messaging systems, all of that stuff, the configuration of our switches and our networks, all of that stuff is part of the environment that the software inhabits and has an impact on its behavior. That stuff is part of the application too. Kind of getting into ideas like infrastructure as code and being able to automate and configuration manage all of that stuff. Software is unusual stuff. In most of human experience, if something's difficult and painful, it probably makes sense to avoid it. On the other hand, if something's difficult and painful in software and you start avoiding it, it's probably just going to get worse. If your release process is ugly and painful and you're releasing once every 6 months, I guarantee you it's going to be more than twice as bad if you start releasing once every 12 months. If you're releasing once every 6 months and that's difficult and painful, the way to tackle that is start releasing every 3 months, start releasing every month, every week, every day, every 30 minutes, whatever it is, drive the cycle time down, and that will force you to address the problems that face you. That will force you to be able to fix the problems and get good at those aspects of your software development process. We need to focus on quality. As I said, we want our systems to be deterministic, reproducible. We want if a test fails, we want it to be telling the truth. If the system says that it's passing, we want that to be telling the truth as well. Done means released. Done means in the hands of users delivering value. We want them to work in ways that are transparent, use technologies that are transparent and gives everybody some insight into where change is in the flow of ideas through the system. And ultimately, this is not the sort of process that you can say, okay, we're going to have a 3-month program of adopting continuous delivery, and we're going to buy a book and hire a consultant and buy a tool, and we'll be there then. No, I believe this is a paradigm shift. I believe that this is a culture change. This is a significantly different way of thinking about software development. It challenges all aspects of software development. It challenges the organizational structures that you set up. It challenges the way that you think about software design and development and release and all of those things. And so we need to start thinking about those and start tackling things in new ways. That means it's difficult to adopt this kind of change. I believe I can give a reasonably compelling argument to kind of back up the ideas of continuous delivery in about an hour. And I think it's actually really difficult to implement this because you've got to be good at lots of stuff. So you need to undertake a process of continuous improvement. If you look at the teams that take this seriously, they're kind of, from then on, they are always experimenting. They're always looking and always reviewing and always being skeptical about what they're doing, and they're trying to improve and refine and get better at every aspect of their development process. This is just me showing off. This is a quote from Forrester Research a few years ago. If agile software development was the opening act to a great performance, continuous delivery is the headliner. I think that continuous delivery is quite widely seen as state-of-the-art for software development process these days. And I think that there are good reasons for that. And those good reasons are that it works. It works better than anything else that we've found so far. When we find something that works better than this, I will adopt it like in a moment. But so far, this is what we found works the best. So let's go into that in a little bit more detail. So we have some developers working on a change. They're going to commit that change to a version control system. And we have a process monitoring that version control system. When it sees a change, it's going to kick off an evaluation of the change. It's going to run a bunch of tests. And what the objective of this at this stage is to give fast feedback. We're looking for very rapid feedback of the quality of the change, and we'd like to have a relatively high level of confidence that if this battery of tests passes, then the release candidate has probably got a reasonable chance of succeeding through the rest of the validations. That's important, and it kind of gives us a balance. It means that there's a trade-off going on here between the quality of the feedback that we're getting and the rapidity with which we get it. As a guideline, I generally advise my clients to aim for a maximum of feedback in about 5 minutes. So even if you've got a big, complicated system, you'd like to be able to commit a change and get feedback and understand the implication of that change in about 5 minutes. There are good reasons for that. That's because if it goes much over 5 minutes, it tends to impose a tax on every commit. It means that developers tend to hold back and not commit so frequently. And that's a problem because the process works best if you make many small changes. So far, what I've described is only continuous integration. It's no more than that. The tests that we're going to run in that commit stage are nearly all probably best placed the products of test-driven development. I think that test-driven development is one of the most important steps. That this too is one of those step changes in capability. And I think that for a quite simple reason. Test-driven development is different from unit testing. Unit testing is the process of testing small pieces of your code after you've written it. Test-driven development is driving the design of your system from tests. And that's a different thing. Test-driven development is primarily about design and only secondarily about testing. So why does that matter? I would argue that the qualities of the properties of high quality software haven't changed much for the last 3 decades. I would argue, since I started doing development, it's been fairly consistent that high quality is considered to be modular software, loosely coupled software, software with a good separation of concerns, software with high cohesion, and software that exhibits information hiding in some ways. And I think those are hard to argue against. There might be some other properties that are valuable too, but those 5 are pretty much inarguable hallmarks of high quality software. What makes us write high-quality software? Well, before test-driven development, the only thing was the integrity, experience, and commitment of an individual software developer. It was down to us. So test-driven development starts from writing a test. We write the test from without having implemented anything. We write the test and we say, okay, we want to make this as simple as possible, and that drives us in a certain pattern of design. It means that we tend to use dependency injection. It means that we tend to write things that are fairly abstract. It tends to mean that we write smaller modular pieces. So what are the properties of software that make test-driven development easy? Well, it's modular, it's loosely coupled, has a good separation of concerns, high cohesion, and exhibits information hiding. It's the same things. So now we have a process, a tool, a mechanism that gives us an impetus to create higher quality. I would argue that test-driven development is like an amplifier on the skills of any software developer. It makes crap software developers a little bit better, and it makes great software developers even better. So it makes everybody a little bit better than they were without it. So I think it's really important. The downside is that test-driven development asserts that the code does what a developer wants it to do, which is a really valuable thing, but is not enough. which is where the rest of the pipeline comes in. So once our commit stage has run all of these little tests that are developed as part of test-driven development, it's going to generate a deployable artifact. We want this to be the same thing as we were going to release into production. Should this release candidate make it that far, we want the same binary. Now we want to evaluate it from the perspective of a user. We'd like a bunch of tests that assert that the behavior is what users would like of the system. We'd like to evaluate it in a production-like environment. We'd like it to be evaluated from the perspective of this external user of the system in a production-like environment, running realistic use cases, realistic interactions. And so we're going to run these high-level functional tests against the system to assert that the software does what the users want it to do. We're going to pull it out, deploy it on an automated basis into a test environment. We're rehearsing the deployment. We're using the same deployment mechanism that we will use in production. We'll run all the tests, and we're going to tag the release candidate in the artifact repository with the results of the tests. I would argue that any regression testing, that any form of manual regression testing is a waste of time and money. It's expensive, low quality, slow, and an abuse of people. We're really not very good at it, and it's really not a very pleasant thing to do, manually just following a script. It's not a very creative thing to do. So we want the machines to do that for us. That doesn't mean that people have no role. If you've got a user interface, you want to evaluate the software. Is it usable? Does it paint nice pictures inside my head? Does it allow me to extrapolate and understand where I'm going to go next? All that kind of stuff. So we can use people for that sort of exploratory testing as new features are added. The system that this example was based on was a very high performance system, the trading system that I talked about. So we did performance testing at 2 levels. We did component level performance testing and whole system level performance testing. Each test would be based on a threshold of performance. It would evaluate the system. If it failed to achieve the threshold that we defined for success, it would fail the test. So we got a pass-fail even for our performance tests. We then would, so far, we've looked at it from the point of view of a developer, we've looked at it from the point of view of a user, we've looked to see whether it's usable, we've looked to see if it performs well. What's left? Well, we'd like to make sure that it works with production data. We'd like to be able to evolve and refine our understanding of our data structures as well as everything else. So we'd like to build that into our deployment tool so that when we deploy the system, it's going to upgrade the data structures and migrate the data at the same time. And so we'd like to evaluate that against production data. What we did was that we would take a cut of production data at the start of every day. We'd anonymize that, deploy that into our test environments, and then every release candidate that went through the process would be started up against that cut of the data. It would migrate the data into the form that it needed. We'd start it up. We'd run a whole bunch of smoke tests against it just to check that it looked like it was still sane. If all of that was done, we couldn't think of anything else to do. So we're ready to release into production. All the time, we're collecting metadata. We're painting a picture of the story of this release candidate. If at any point any test fails, we stop there and then and we discard the release candidate. We don't try and patch things up partway through. The way to fix things is that we go back and we commit a change back into the pipeline and run it through again from the beginning. We do each step once and only once, so that's efficient. This whole process is called a deployment pipeline, and this is one of the mechanisms that allows us to carry out these experiments, to evaluate our changes. We can, if we're working in a regulated environment, we can kind of build the compliance into our deployment pipeline. We can make assertions in here that will make us certain that we can't break the rules. This is a very powerful tool, very powerful technique. One of the pushbacks that I sometimes get is, okay, that sounds really nice for small projects, but it can't possibly scale. My answer for that is Google. So Google have decided, on the whole, the vast majority of their projects, they put all into one repository, and every time anybody makes a change to any of them, they build them all together, and they run all the tests together, and they evaluate them all together. They have more than 60 million builds a year and growing exponentially, more than 100 million lines of code. There are more than 20 commits per minute, and they run 100 million test cases a day. So it scales quite well. The other pushback that I get is that you're talking about releasing how often? You must be mad. Our releases are a nightmare. It's terribly scary. We can't possibly encompass that level of risk. My answer to that is the Amazon build process. So has anybody used Amazon recently? Which version did you use? That's a stupid question which even Amazon couldn't answer, because on average, Amazon are releasing a change into production once every 11.6 seconds. On average, that change, once every 11.6 seconds, goes to 10,000 or more servers. Since they've been doing this, they've seen a 75% reduction in outages, a 90% reduction in the time spent recovering from outages, and less than 1 in 1,000% of deployments causes any problems anyway. And they've got instantaneous rollback and a reduction in complexity overall. The last pushback that I sometimes get is, okay, that's nice and easy for simple websites like Amazon and Google, but my technology is really hard. And my answer to that is the HP LaserJet firmware. So this is the firmware in all HP LaserJet devices. And they kind of did they did an analysis of their software development process. In 2008, this is the picture, and it wasn't a pretty picture. They had a massive backlog of requirements. The backlog was so large that the business had literally stopped asking for anything new from the software development organization because they knew they would never get it. At which point they kind of said, we ought to stop and just think about this for a minute. At this point in history, 5% of their global development of it, I think they had a team of about 450 people worldwide. 5% of that effort was spent on doing innovation, what you and I would just call any new feature. 5 times that amount of effort was spent on porting code between branches and product support, which says that they probably had a quality problem as well. So they did pretty much what we've just done. They've just said, this isn't working. Let's go back to first principles and figure out what we should do. And in parallel, kind of independent of the stuff that Jez and I and other people were doing on continuous delivery, they kind of evolved a process which is indistinguishable from continuous delivery. I think that in itself is an interesting concept, this idea, this sort of parallel evolution. Given the same, if you're taking this rational, empirical approach, you end up with something that looks almost the same. And they came up with this process independently. Afterwards, they have a really different picture. They got 8 times as much effort doing new stuff, valuable new stuff. They spend a lot of time doing different things that they weren't doing any of before, spending a lot of time writing automated tests, maintaining the pipeline, all of that sort of stuff that they weren't doing before, but it pays back. They're doing more stuff. The bottom line is that overall development costs were reduced by 40%. Programs under development were increased by 140%. So costs go down while the amount of stuff that they're doing goes up. Overall cost per program down by 70%, and the resources driving innovation was up. All of this is described in this book, which I recommend to you, particularly if you're in a big organization and you're interested in kind of managing cultural change. It's not a deeply technical book, but it's an interesting one. So what's my point? What's my argument? I believe that continuous delivery changes the economics of software development. We are not talking about 5 or 10% improvements in productivity. We are talking about orders of magnitude change in productivity. The numbers that come back from the industry are staggering. We're starting to collect data that says that organizations that practice these kinds of approaches to software development make more money than organizations that don't. I believe that continuous delivery will have an impact on you. You will either start practicing it and start doing some of these things, or ultimately your competitors will, and when they do, they will beat you because they'll create better software faster. I think it's that stark. I think we've found the answer. I think we've found what really works. Here's a summary of some of the data. So, data from peer-reviewed surveys, scientifically rigorous statistical analyses of software projects, first time in the history of software engineering, says that you're twice as likely to exceed market and profitability shares if you practice these kinds of disciplines. You're 50% higher market cap growth over 3 years, and 66% of organizations that practice these sorts of development approaches see a dramatic improvement in the quality of their software. The only question I have about this is I don't know what the other 34% of people are doing, because I think it's better than that. What characterizes these high-performing organizations? Well, doing DevOps back practices, continuous delivery, these sorts of things. Organizational culture and climate for learning. But the number one predictor for this kind of success is job satisfaction. So, Let's just review that. If your organization practices this kind of approach to software development, you're probably going to make more money, you're probably going to grow your organization better, you're probably going to have an improvement in quality, and the people working for you are going to have more fun. I think that's pretty conclusive. So some of the organizations that practice continuous delivery, I think this is a tiny, tiny sample of people that have talked about it publicly. And it's not really representative. There are lots more organizations these days than this. But there are some organizations on here that are probably the ones that you'd expect, and some that are probably a surprise. The first time that I saw SAP on here, I was surprised because I think it's a fairly traditional organisation, but they have areas of working where they're seeing dramatic improvements in the quality of their stuff by applying these techniques. As a sciencey nerd, I was particularly delighted to see NASA on there. The Curiosity rover, the software of that amazing spacecraft. You have a sledge, a rocket-powered sledge, aerobraking through the atmosphere of Mars, hovering above the surface of Mars, lowering the Curiosity rover to the surface on a crane. The software for that system was written using the techniques that I've described, continuous delivery, because it had to work. There was no backup, there was no redundancy, it had to work first time. And so they wanted to apply some proper engineering discipline to the process. And that's me done. So thank you very much. I'd be happy to take a few questions. I'm about 5 minutes over.
When you talk about continuous delivery implementation, you focus on the code itself you develop, but continuous delivery infrastructure is taken for granted. It's like it exists and it works and you can automate everything. But usually when you start implementing continuous delivery, continuous integration, stuff like this, you start investing your time and resources to develop continuous integration system instead of developing your application. And the more it goes, you need then to develop continuous integration system for your continuous integration system, so your main application keeps working and so on. So is this included in this measurement of success for developer companies? My question.
Yes, it is, but I wouldn't do it the way that you've just described. So I am not advising you to all go home, say to your businesses, we're not going to do any features for 6 months, we've got to build a continuous integration infrastructure. No, that's not the way to succeed. So how do you do this? You do it incrementally, you do it experimentally, you do it in small changes, the way that you do everything else. So the first story for a new development is probably about establishing the commit cycle, and it would be nice to be able to deploy that into a production-like environment, which is probably trivial. It's probably just a matter of copying some binaries and writing a shell script to do something. You can do it in 5 minutes. An acceptance test, you can come up with an acceptance a outside view of the system very quickly that allows you to do that. It's probably a bit more costly to get that infrastructure in place. But once you've got that infrastructure in place, you can go with that for quite a while in development, and you can use that. Then over time, as you get more complex stories, you start fleshing it out. What you tend to find is that what drives you is the feedback cycle. So you carry on working with a really simple implementation for a while, and you get that established and working effectively, and then you find that your feedback's starting to slow down because you've got more tests. So now you want to think about parallelizing things, and so you start to run those in parallel, and now you think about maybe building out your build grid to have more computers and do that. And so over time, you get more and more complex infrastructure until you get really quite sophisticated systems to manage this stuff. But you do that in small steps, and the cost of those steps is smeared out between many, many, many stories. It doesn't mean that there's no cost. I mean, one of the downside of, if downside it is, that one of the implications of continuous delivery is that you are going to spend more time on things like getting tests running and, responding to breakages and keeping your infrastructure going and deployment automation. But that is paid back because you don't spend as much time chasing down bugs in production because you don't have as many. You have dramatically fewer bugs in production. You spend time doing different things, which is kind of what the HP slide showed us. It's not that you don't do lots of work, it's that you just trade that off. The other thing is that you tend to spend a lot of money on hardware because it takes a lot of, as you grow the sophistication of your test environments, they tend to lose up a lot of hardware. The LMAC system, the trading system that I used as my model here, was probably an unusual thing because it's quite a high consequence system. There's lots of money flowing through it. It's quite a technically demanding system. But we had probably about a quarter of the amount of hardware focused on the development and implementation as we did in production. There's quite a lot of test hardware. So absolutely there are costs to this and there are expenses, but my experience across the board is that it's paid for itself. In general, when I work as a consultant, I advise clients on trying to do this kind of thing. And in general, I advise my clients that they can usually expect, if they're starting from not doing any of this stuff, there's going to be a cost. There's going to be an activation period when they're going significantly slower than they were before they started, while they're learning the skills, adopting the technologies, getting the stuff in place. And that activation energy I usually estimate is probably in the order of about 3 to 4 months, after which you will be going faster than you were before. And from then on, you will start to accelerate. So you're probably getting a payback maybe 6 months down the line in terms of overall. So if you've got a project that's shorter than 6 months, maybe this is the wrong, and you've already started, maybe this is the wrong thing to do. But if you're starting from scratch, the startup costs are cheaper if you've got the skills in the team. But there is a learning curve. This is a different approach.
Hi, I have a short question. We all like to bash workflow, the pattern, the methodology,
yep.
But do you think it could have been possible to invent Agile at that time, at the 70s, and apply it?
Yeah, so I think lots of people actually practiced it and it applied. So if you look at the way in which the software for the NASA program, for the Apollo program was developed, that was really quite an iterative approach. It wasn't a massively planned approach in many ways. I think if you look at lots of successful software projects in history, there's a great, so one of the other things that I often talk about, I run training courses on, is test-driven development. I'm a big fan of test-driven development, as you can probably tell. And I did a bit of research into the history of test-driven development, and one of the things that I found that delighted me was a paper from a chap that was talking at a NATO conference. This was the first time that the term software engineering was ever used. And this conference was intended to define what software engineering meant. And at that conference, this chap wrote a paper that precisely describes test-driven development. It says that you should use testing to drive the design of your software. And he describes all of that. What on earth happened? We missed the point and we didn't do it. We picked up bloody waterfall and then ignored test-driven development. That was a big mistake. So I don't think any of these ideas are profoundly new. I think what's happened is that we've tried lots of different things and we've been able to eliminate some things that don't work. And we've learned things. There's still lots to learn. There's still lots of effort that's required to do these things well. But I think there are constraints now. There are boundaries. We know that it must be empirical. We know that it must be iterative because we're not good enough at guessing what's going to come. And so working in ways that allow us to learn and adapt and refine what we're doing is kind of fundamental to building anything really complicated, I think.
What do you think about distributed development?
Distributed development.
What do you think about? We have a central continuous delivery machinery.
Yep.
In Germany, in US, or in Czechia, or in India, or something else, and all over the world, developers are committing to this system.
So
that may work.
Yeah.
I don't think not,
so yes, but it's a complex question to answer. So there are lots and lots of parts to this. You can make continuous delivery work in a variety of different circumstances. The crucial circumstance, the crucial thing is to kind of align teams with deployable units of software that are independently deployable from one another. Scope your deployment pipelines to deployable units. So, that's a good idea. Where you place that in the world, what the boundaries are between teams is less important. I think one of the strategies for success when you're talking about a geographically distributed team is to make sure that you have all of the functions for the team in all of the places. You don't have testing in India and development in Germany, because that's a problem. That means that the feedback's really poor between those two different groups. You have bits of testing in Germany, bits of development in Germany, bits of deployment in Germany, and you have the same in India or whatever there is. So I think that's the model for distribution. There are many, many, many examples around the world of very successful projects that are developed using continuous delivery in globally distributed teams. This is a very effective strategy for doing that. It's even where a deployment pipeline is shared across geographic boundaries, that works very well. I've done different aspects of all of those successfully. So I think there's nothing that says that, although there's an awful lot of complexity and devil in the detail in terms of what makes sense in terms of how you carve the software up into pieces, what are sensible boundaries for software, whether you treat it as one big thing or many small things. All of those work, but there are different trade-offs in the strategy.
So you talked about that after a commit, is like you recommend to get the feedback to the developer in like 5 minutes max.
Yes.
So and also the concept of dependency injection. Just a question about like mocking stuff.
Yeah.
Then because if you want to run them that fast, you have to start with mocking and dependency injection. Is it in your perspective better to mock almost everything, or just the modules that may have side effects like database and where you have to start setting up, or even the smallest pieces, which more like in an output? Or
so I would use mocking quite widely. So I think at the technical level there are kind of 3 different sorts of unit tests, TDD style tests. You're going to be evaluating 3 different classes of things. You're going to be invoking some behavior in some code, and you're going to be checking for some sort of return value or an exception. You're going to be invoking some behavior in code, and you're going to be evaluating some change of state, something like opening a connection or something like that. And you're going to be invoking some behavior in code, and you're expecting it to interact with some dependent object, where the dependency injection comes in. So the last one is where mocking lives. I think roughly in order of frequency, you're going to have more of the first type, a few less of the second type, and even less of the third type. I think that one of the tricks to high quality TDD is you use the feedback that you get from the design, from the complexity of the test setup to inform your design decision. So if you're finding it's difficult, if you're creating a component that needs to have lots of mocks, that's telling you that there's something poor in your software design. It's not the test's fault or the mocking's fault. It means your software design is inappropriate and you haven't got the separation of concerns right. You should be teasing things apart and modularizing the code better. So you kind of use that feedback to morph your code into a better shape. When you get to that situation, usually what you end up with is each component probably has only 1 or 2 different dependencies to interact with, and therefore it's relatively simple to use mocking for all of those things. And so I'd use it fairly widely in that context. But you do have to listen. If you've got horribly complicated mock setup, what it ought to be telling you is, I've got to go back and review my design because there's a problem there. Thank you very much for your time.